range of Peru to be 4.6 petabytes per area.
Okay, so today we're going to take a step backwards, quite a bit backwards, to what we did way back in chapter 1, maybe 2. We're doing some limits today. However, this is going to rock your world because it's going to allow you to solve a whole bunch of limit problems that we couldn't solve before. This is called L'Hopital's rule, and it was discovered or invented or whatever you want to refer to that as by a guy named L'Hopital, which translates in French to the hospital. And it allows us, so let's back up. You remember when we were doing limits and we had that process when solving a limit. The first thing we would do is plug and chug. If plug and chug didn't work, then we would try to algebraically manipulate. If algebraically manipulate didn't work, then we would just say, does not exist. There is no limit. We can't find it, blah, blah, blah. L'Hopital's allows us to solve limit problems that we couldn't solve before based on one simple idea. And the question you're probably asking yourself is, why are we waiting till now? You'll understand once we get into it because L'Hopital's rule involves a derivative. Okay, so let me give you the fancy schmancy calculus speak first, and then we'll talk about what this means. That probably doesn't make much sense to you. However, I'll try to put it in English, and the application of this is really simple. We're going to get into something called indeterminate forms. Indeterminate forms. You've seen these before. You just didn't know they were called indeterminate forms. If we can get to the indeterminate forms, then we can apply L'Hopital's rule. And L'Hopital's rule is very simple. It says, I'll put this in English for you, if you try to take a limit and you get an indeterminate form, that's okay. Just take the derivative of the top and the bottom and do it again. It doesn't work, do it again. It doesn't work, do it again. And at some point you're going to say, I either have a limit or I have no answer. It is possible to still get no answers. And again, this is a little confusing, but once you see it in action, it'll make a little bit more sense. The thing I want to stress over and over again is that it is not a quotient rule. We're not doing quotient rule here. We're going to make it really simple. You're literally just taking the derivative of the numerator, the derivative of the denominator, and plugging and chugging again.
Does this say indeterminate, like, is that just an N?
Yeah, that's a, I had a little,
No, it's okay.
I had a weird moment at that point in time. Didn't want to erase. Okay, we're going to start with two indeterminate forms. 0 over 0 and infinity over infinity. As I said, you've seen those before. We did limit problems a while ago where you plugged and chugged and all of a sudden you got 0 over 0. Then we tried to algebraically manipulate. A lot of times it worked out because that's what we were doing at that point in time, but sometimes they didn't. And when they didn't, we just said DNE does not exist. Now, L'Hopital's will allow us to go a little bit further. Okay. Everybody good with this? Okay. Example number 1. Couple things to consider now is that you can't automatically assume that L'Hopital's applies here. You need to check it every single time. So we're going to stay with the same format we used before. We're going to plug and chug. So do that. Plug in 0 and tell me what you get.
Undefined?
Why?
Because you have a 0 in the denominator?
No, you got to do more than that. You got to plug it in the numerator and the denominator. 0 in the denominator is not enough to apply L'Hopital's. You have to get one of the indeterminate forms. So what's the numerator become?
0 as well.
0, right. So we have an indeterminate form, 0 over 0. Check. We're good to go. And again, you have to check that every time. So if we were doing this back in September, then we'd say, okay, now we need to algebraically manipulate. And we look at that and you say, I can't algebraically manipulate that. There's nothing to factor out, nothing cancels, there's nothing I can do to simplify that algebraically, so we would just say DNE, done, and move on. With L'Hopital's now, changing colors, because I can, we now take the derivative of the top, derivative of the bottom, and do it all over again. Dimitri, what's the derivative of the numerator, please?
Negative 3 sine x plus 5.
How do you do? Dimitri, what's the derivative of the denominator?
2.
Well done. Let's give it up for Dimitri. Plug und chug. What do you get?
5/2.
5 over 2. Done. Okay? Problems. Today we're going to look at 3 indeterminate forms. We're going to do a couple of more examples of the easy ones, then we'll get into one ugly one. It's not very common, but you still need to see it. Any questions on this? Beautiful. I'm going to put a little yellow cloud around this because you have to remember to test your functions to make sure it's an indeterminate form. Let's see. We don't want to do a trig one, do we? No. Let's do, how about an infinity one? This will be fun. Example number 2. Limit as x approaches infinity of the natural log of x over the square root of x. What's the natural log of infinity? Say again? Infinity, good. What's the square root of infinity? Infinity. Therefore, we have infinity over infinity. Check. That is an indeterminate form. I'm good to go. Now we can apply L'Hopital's. I did the work up front to guarantee that L'Hopital's works. So therefore, I can apply the theorem. Applying the theorem means that I take the derivative of the numerator, derivative of denominator, do it again. Okay, go ahead, do it again. Ooh, this is a tough one.
So, number x.
This sounds better, but then I think of some of the stupid things that I would say out loud and get myself in trouble. What's that? No, I would be hard to, but I think that's the less destructive. But you can't. It's just gonna fly out of your mouth. What, gag yourself?
Well, yes,
Cover your mouth.
exactly.
Nobody can hear what you're saying.
Whatevs.
But if you had an interview and you couldn't do it that way and just like flirt, you can't.
Yeah, you're in a job interview and the guy interviewing you has like a booger hanging out of his nose. You're gonna say like, this dude's got a booger hanging out of his nose.
But
Little
what
loser.
about never speaking again? How's
never help with you.
I mean, my thoughts are weird. We
Sign
like eat it
language,
and
you
like
can
wait,
also
what?
write it out.
Haley, what do you got?
You just speak.
Final answer?
You just speak.
Okay, go ahead. We'll wait. Okay, Mr. Mamby Pamby.
I moved this to the top. I can destroy this equation.
Progress?
From the one nothing. Yeah, because this is the same thing as x to the one. X to the one. Like when I first said negative one, the bottom part, and then you move this to the top.
Is this becoming an algebra problem or a calculus problem? Because I'm seeing most of you are doing the calculus okay. Duncan, what's a derivative of natural log?
How to put this into words? Like the derivative, or like n prime over n. That is
What's the derivative of the natural log of x?
1 over x.
Beautiful. This is the same thing as x to the 1/2, in case you didn't know that. What's the derivative of x to the 1/2?
1/2 x to the negative 1/2.
Okay, how many people got to that point? And then you tried to plug in infinity again and all hell broke loose, yes? Okay, so let's do some algebra. Yes? Okay. Dividing by a fraction, same thing as multiplying by the reciprocal. Yes? X to the 1/2 divided by x to the first is x to the negative 1/2, which brings it back to the bottom. Then I plug and chug. I should get an answer now because my numerator is a constant. What is 2 over infinity?
Oh wait, I did it wrong. Is it wrong?
0, correct. As a denominator gets very, very big and the numerator stays constant, the number gets closer to 0. 1 over 10, 1 over 1,000, 1 over 1,000,000, 1 over 10 million. Smaller, smaller, smaller until it approaches 0. So hopefully the concept of L'Hopital's is pretty straightforward. However, this problem illustrates that the application can sometimes be a little nasty. Okay, there's not a lot of calculus going on here. There's some calculus here when we took the derivative. And there's some calculus, kind of some calculus, when we took that final limit. Everything else is algebraically manipulating that, which can sometimes be rather challenging. Questions so far? Okay, beautiful. Next example. Let's see. Let's do this guy. Wait. Number 3. What are we going to do? Let's do this one. Okay, go. This one you're on your own.
you guys are writing what you're thankful for, like, we're doing for this.
Yeah, there seems to be a juxtaposition.
More than 0, 0, showing.
I'm so
This
thankful.
just shows.
No, we can't even believe it.
I'm very thankful for you.
0 squared.
0 and 1.
La Hospital.
The negative exponent is so it'd be like 1 is 1 plus 0
You
is 1.
need a negative 0. You need a negative x is negative. Or negative 0 is 0. It's just e to the 0 is e to the 0. It's 2. But then it's 1 minus, and then that's 1. E to the 0 is
Why is it minus?
E to the 0 is 1. Because when you derive it,
E to the 0 is 1.
e to the x derived equals e to the x. But e power negative x.
Derived is equal to negative.
No, it derived that is negative e to the x. It is.
Why are we taking this derivative? We're literally just plugging in 0.
Yeah, but then if you just plug in 0
2 over
rest-
0.
If you just plug
There
in
is no negative 0 in there.
Wait.
Negative 0 is the answer is 0.
No, wait, you're right. You're right.
Actually, yeah. So we're just plugging
Yeah,
it.
that's right.
So it's 2 over 0.
But what's the e to the negative exponent?
But it doesn't make it an indeterminate form. Indeterminate forms have to be 0, 0, 1.
Yeah, that means that it's not applicable.
Yeah, exactly. So it's not like
It would be more difficult. It would be
right now. Yeah, I've been so passionate about things right now.
Beautiful. I'm proud of you guys. The reason I'm proud of you is that from what I can see, nobody just dove in and started taking the derivative. So you listen. What do you have to do? You got to check to see if that's indeterminate. Is it? No, it's 2 over 0. Right? Okay, so now we need to address that. So what is 2 over 0 equal to? If we go back to this problem, we talked about the fact that as the denominator gets very, very big, the fraction and the numerator stays the same, the fraction approaches 0. Okay, so here in this one, we've got a denominator that's getting very close to 0 as the numerator stays the same. So let's think about that. You've got 2 over 100. You've got 2 over 10. You've got 2 over 1. You've got 2 over 1/10. What's happening to that fraction? How big? Good. Good. Don't automatically look at every limit problem now and assume that it's L'Hopital's. You got to test it to see if you get 0 over 0 or infinity over infinity. Okay, last example, and then we'll move on to something different. What happens? Our third indeterminate form is the following. Let's do 0 times infinity. If we get 0 times infinity, we're going to consider that an indeterminate form. Okay? Why is it in an indeterminate form? Well, one side of the argument says 0 times anything would be 0. The other side of the argument says when you multiply anything times infinity, it just continues getting larger and larger. So we end up getting a contradiction here. So what do you do with a problem that when plugging and chugging, you get 0 over infinity? We're going to use this little guy. It'll be easier to see if we just dive into an example here. Okay, so limit as x approaches 0 of x squared times the natural log of x. Now, full disclosure, this is a little sloppy mathematically because, you got to be concerned about natural log as you approach 0. You're going to come from the positive side because you can't put a negative number in the natural log, et cetera, et cetera. Okay. What's the natural log of 0? You got a calculator handy? Type it in your calculator. What's it equal? I don't know. That's what I'm asking you. I don't know what I'm doing. I'm typing it. I understand. While dealing with separation, okay. What is it? Say again?
You get negative.
Oh, Gabrielle, you're saying it's infinity. What's your calculator say it is? When you type in the natural log of 0, what does your calculator say? Error. Okay, so now graph the natural log of x. Put natural log of x into y1. Zoom 6 that puppy. Refresh your memory on what the natural log graph looks like. And based on that picture, what should it be as x gets close to 0? We cannot take the natural log of 0, but we're dealing with limits here. So we're getting close to 0. What's the natural log graph look like? Graph the natural log of x. Change that to your own information. Okay, so refreshing your memory, the y-axis is an asymptote for the natural log of x. It never touches it, that's why you can't take the natural log of 0, but if we get very close to 0, what is the natural log of x approaching? Negative infinity, okay. Which is close enough to infinity. Infinity, negative infinity, it's interchangeable. If we get this indeterminate form, it's very simple. We're going to take that problem and rewrite it. How do you rewrite it? You create a fraction out of that equation. So it's a fairly simple idea. It says that if you have f of x times g of x, that's the same thing as f of x divided by 1 over g of x. Okay, let that sink in for a second. Dividing by a fraction is the same thing as multiplying by the reciprocal. So I'm going to choose one of those expressions. Let's use colors here. I'm going to choose either the light blue function or the neon green function and choose to send that to the denominator. Which one? You can do either one. You'll get the same results. However, what I try to do is I send the less complicated function to the bottom, which would be x squared in this case, in my opinion. I think x squared is less complicated than natural log. Does that mean that you can't send the natural log of x to the bottom? You definitely can, but I have found from experience that it'll make your life a little bit easier. So I'm going to rewrite this as the natural log of x divided by 1 over x squared. Okay? And now you see what happens. Now we end up with infinity over infinity, which is something we've already done. I plug in 0 here, I get infinity. Technically it's negative infinity, but roll with it. If that goes to 0 in the bottom, then that's going to approach infinity. I have infinity over infinity. L'Hopital's applies, take some derivatives, we're good to go. Okay? You can finish this problem on your own, yes? You don't have to do it now, but you don't need me to do this. Hopefully. Okay. Derivative of natural log of x is 1 over x. That's x to the negative 2, negative 2x, and negative, blah, 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 plug and chug, get your answer. Okay. There are other indeterminate forms. We're not going to bother with them because they very seldomly, if ever, pop up. So we're going to gamble that they don't show up. Question?
You would take the derivative of the natural log of x over 1 over x, right? Or would you take the derivative? Would it be the same?
No, you would take the derivative of your two expressions now. This is one of them. And this is the other.
So you want to take their extra.
No. Because we adapt this into something that's kind of a mediocre indeterminate form into something that is one of our true 0 over 0 or infinity over infinity.
So, like, if you have a 1 over x, oh wait, that's going to be, wait. Should you write, like, negative infinity over, is it wrong if you write negative infinity over infinity?
No?
Okay.
We good?
Wait, so what does that mean?
What does what mean?
Does that mean that 0 times infinity is equal to negative or infinity over infinity?
We don't know what it's called an indeterminate form because we can't determine what it equals.
So
You go back to the argument of.
but like they're both indeterminate. They
Okay.
can set them equal, right?
We've had this argument before, but I'll ask it again. What's that equal to?
I say 5.
What's that equal to?
I don't know.
There's like three.
Yeah.
There's like three answers. Just give me one.
What?
One, right? Because it's a number over itself.
The same thing.
Beautiful. What else does it equal?
0.
Because?
Because it's because 0 is on top.
Right. Numerator is equal to 0. Number 3?
Not defined.
Undefined because the denominator is 0. Which one is it? Yes.
Who knows?
Very good. Right. We don't know. It's an indeterminate form.
But like because you can't determine it, you like if you can algebraically manipulate 0 times infinity to become infinity over infinity, doesn't that make them equivalent?
Well, multiplying something with 0.
He's not asking you.
Sorry.
Well, yeah.
So you want me to figure out how I can prove that these two things are equal?
No, it would be infinity.
What's wrong with you, son? There's no way that's going to happen. Okay. We're just going to erase this like it's not even here.
Okay.
Okay? Because that's just going to...
The board wants you to elaborate.
See, lots
It
of
asks
help.
questions.
It's curious about. Yeah. Okay.
I have a question.
Yes.
So, this doesn't, I'm aware that this doesn't matter at all because it has the same answer, but for like curiosity, right? So, if you have any number squared at all, I mean, unless it's like imaginary or something, like it equals a positive.
We're in a real number system.
Yeah. So, 0, 1, like something divided by 0, right? You could say, yeah, but it approaches infinity, right? But it could also approach negative
Are you
infinity.
talking about the value of the function or the limit?
I
They're
guess-
two entirely different things.
I guess the limit, because it never reaches infinity, but...
Well, if you want to talk about the limit of 1 over 0, then that's going to be different than the value of 1
Let's
over
say the value 1 over 0, right?
Okay?
We say it's...
There is no such thing.
Okay. What's the limit? Because that's what we get infinity.
Infinity.
Yeah, so is it not negative infinity though? Because isn't 0 neither negative or positive?
It depends on the function.
Yeah. Oh, I guess the direction it's coming from. Oh, that makes
Correct.
sense.